Okay, so I've just got some 9 problems here. Just to mention the bounds, tomorrow, Professor Paul Horn will do the bound that the domination is most 1 plus, log delta plus 1 over delta plus 1. So that'll be tomorrow in the probabilistic proofs. I think you'll present that, or at least you'll know how to do it. But let's maybe look at some elementary domination. So I've got these 7 problems. Some we'll do together. So the first one was that very basic property we're going to look at. 2 is just to make sure you be familiar with minimal dominating sets. 3 is also will be very easy. 4, I'm going to present to you a very simple algorithm for a tree. It's really a simple algorithm, but we'll just go through that. And then we can see, we may go through 5. 5 is, how do you determine the domination of a graph? And we'll take an example. I've taken this generalized Peterson, and we will prove that the domination number is equal to 5. And then question 6, it's just a small little exercise in domination. We'll prove that if a graph doesn't have P4, C4 as induced subgraphs, then it has a dominating vertex. And so example 7 and 8 are just ones of diameter 2, very, very restricted graphs. But exercise 9, we're going to give a construction, there's many, of a family of graphs with diameter 2, where the domination number could be arbitrarily large. And we'll do some constructions there. So I wonder if I should, if the best thing is we can work together, but you'll have to interrupt me. So maybe I can start with some of these. So maybe let me stop sharing and start sharing on the first property. Remember, we looked at minimal sets. Now, domination is super hereditary. So it's a very, very useful property of a minimal P set, that it's minimal if only if it's one minimal. Because you don't have to check every proper subset, you just check those of cardinality 1 less. So let's just prove number 1 first. So let me stop sharing and then start sharing with my slides. Let's see if I can get it up. So let's start sharing this. Okay, let me see if you can, hopefully you can see that. So what we showed in the first part is this property of a P, hereditary or super hereditary. And in this case, we're looking at super hereditary. In other words, think of domination, and any superset of it is a dominating set. And what we want to prove is that for super domination, minimal is the same as 1 minimal. So let's prove that, and you can just interrupt me. So we'd like to show that in general, you give me any property that's super hereditary. And I want to show that that set is minimal, I just need to look at 1 minimal. Because that's very useful for domination. So let's take our example. Let's take, of course, every minimal P set means every proper subset is not a P set. So in particular, every 1 minimal set wouldn't be a P set. So it's P minimal implies 1 minimal. But the other way around is not so obvious. We need the super hereditary property. So let's pick a set which is a P set. It has property P. Again, think of domination. And it's 1 minimal. That means that if you remove any vertex, you no longer have that property. And let's prove that the set is also minimal. In other words, if you give me any proper subset of S, it will not have the property of a P set. So let's pick any subset S prime and show that S prime is not a P set. And S prime may not have cardinality 1 less. It could be a lot smaller. If the set S prime is 1 less, then it doesn't have the property, because that means that because S is 1 minimal, that means you remove any one vertex, the resulting set will not be a p set. So in this case, if S prime is one less, that means that S prime is obtained from S by removing one vertex. And we know that S is one minimal, which means that S prime is not a p set. So by definition of one minimal, we're fine. The problem is, what happens if the set S prime has cardinality less than S minus 1? So let's look at that case. How do we prove that S prime is not a p set? Well, we have to use the superhereditary property. So what we do is, from the set S prime, we just pick a superset of cardinality S minus 1. So let's suppose to the contrary that S prime is not a p set. Now remember, S prime is cardinality less than or equal to S minus 2. So let's pick a superset S prime of S prime. So S double prime is a superset of S prime, but I want it to be a proper subset of S. And I want S prime to have cardinality S minus 1. Now, by the superhereditary property, the set S double prime also has property P. Because if S prime is, we're assuming that S prime is a P set. So if S prime has property P, every superset has property P. So we know that the set S prime is a P set, but it has cardinality 1 less than S. And that contradicts our supposition that S is one minimal, because one minimal means that you give me any subset of cardinality 1 less that is not a P set. So by supposition, S double prime is not a P set, but it is a P set, which is by our supposition. We get a contradiction. So that immediately proves this property, that if you've got a superhereditary property like domination, then if you've got to check whether the dominating set is minimal, all you need to do is check that it's one minimal. All you need to do is check that for any vertex in S, if I remove S, I no longer have a dominating set. And that's exactly what we did with Auer's lemma and Auer's theorem. So that's the first property. And then we needed that to prove the other result. So any questions about that? So it's just a very elementary property of dominating sets, but you can be a bit more general. You can prove for superhereditary. For any property that's superhereditary, you've got this property of minimal sets. So maybe before I use my iPad and we do some of the actual exercises together, maybe I can jump a little bit since I've got my slides open. Can we look at, if you don't mind, let's go to trees. So what we've proven, what we've just proven now is that this property of dominating sets. A dominating set is minimal if and only if for every vertex, D minus V is not a dominating set. You don't have to check every subset, only those subsets that are cardinality 1 less. So let's just take trees. If you don't mind us going through, there's some classes of graphs where it's very easy to work out the domination number. Some are very difficult. Like, as we said, planar graphs, max degree 3, or bipartite max degree 3, etc. But trees are extremely easy. So I'm going to give you a very simple algorithm. And just stop me as we go through it. I won't explain everything, but we'll just talk our way through it. So remember, trees are connected graphs with no cycles. And what we're going to do in this algorithm is we're going to root the tree, which I'll come to in a moment, but a leaf is a degree 1 vertex. Its unique neighbor support vertex, we don't really need that, but strong support, we also don't really need. But what we're going to do in our algorithm is let's root the tree. We're going to distinguish one vertex, pick any vertex. And we're going to lift the tree up on the root and just dangle everything down. And we'll have different levels depending on their distance from the root. So for every vertex, the parent of that vertex will be the neighbor on the unique path from the root to V. Every other neighbor of V will be a child of V. And a descendant of V will be a vertex U different from V, so that the unique path from the root to U passes through V. That's a descendant of V. Every path, the unique path from the root to that vertex passes through the vertex V. Then that vertex U is a descendant of V. It may be a child, but it may be a grandchild or much further away. And we'll let DV be all the descendants, and we can often look at what's called DV is the set consisting of all descendants together with V. Now, what this algorithm does, now there's many tree algorithms, but the one we're going to look at, I root the tree and I'm going to look at the vertices furthest from the root. And from the bottom of this tree, I'm going to try and dominate by pushing vertices up. If I can dominate from higher up in the tree, I'm going to do so. So let me be a little bit precise, and then we'll be vague again. So, as I said, we're going to draw the tree from the root downwards, and I'm going to label the vertices, the roots number 1. Then all children of the root have the next layers, 2 up to the degree of 1 plus 1. And then you label vertices from the vertex 2, you label its children. And then the vertex 3, you label its children. And eventually everything will be labeled. So the vertices with the largest label are furthest from the root. Okay, let me just give you a picture. So you've got your rooted tree, you've got your parent array, which will tell me what the parent is. So here's an example. There's a rooted tree. I've rooted at vertex 1. And then I label first its children, 2, 3, 4, etc. Then I go to 2, I label its children. Then 3, and I label its children, 6, 7, 8, etc. And then you've got your parent array for any vertex, let's say vertex 8. The parent array tells me what's the parent of 8, which is 3. So whether you use a computer, you use the parent array or the picture, that's what, you can either do the picture or the parent array. Now, what we're going to do to find a tree algorithm for domination is we'll start at the bottom. And we're going to dominate by, if at all possible, dominate with the parent. That's essentially what the algorithm does. So let me be more precise. You start with the vertices with the highest number, in this case n, then n minus 1, n minus 2, etc. And you do the following. So let me do the following. Initially, you put everything as bound, which means if it's bound, you've still got to dominate it. And as the algorithm progresses, you change the label to, it could stay bound or free or required. If it's required, it means you're going to have to put it in the dominating set. If it's free, you don't have to dominate it. So what we do is the following. We start with vertices from n, the vertices furthest from the root, then n minus 1, and so on, until you get the root. And what you do, and I'll just define it, and then we'll look at an example. Everything's labeled bound. If it's labeled bound, it needs to be dominated, but you don't put it in the set, you're going to put its parent in. So you change the label of its parent to required. And that vertex I that needs to be dominated, you label as free, because its parent's going to dominate it. And in the algorithm, as soon as you get to a vertex with label required, you immediately add it to your set. And in that case, when a vertex is put in the set, its parent, if it had a label bound, which means it needs to be dominated, you can label it free because its child's going to dominate it. And that's what the algorithm is going to do. So let's take an example. Well, let's go through it. What you do is you've got your tree, rooted tree, everything's label bound. And what you do if a vertex is bound, you put its parent as required, and you label the vertex as free. If the label of vertex is required, you've got to add it to the set. And in that case, its parent, if it is bound, becomes free. And finally, when you get to the root, if the root is bound or required, you have to add the root to the dominating set. So let's take an example. What we do is initially in the rooted tree, you put everything as bound, which means everything's got to be dominated. And we start sequentially with the vertices at the bottom, 15. If a vertex is bound like 15, what you do is you change its label to free, and its parent becomes required. And you do that for the vertex 14. It's bound, but you change it to free, and its parent 12 becomes required. And with 13 too. So those vertices, you change their labels from bound to free, and the parent's required. Then you move on to vertex 12. If it's required, you have to add it to the set. When you add it to the set, its parent becomes free because it now is dominated from its child. So as soon as I've dealt with the vertex, I color it in. So the vertex 12, when it's required, its parent becomes free. Then I move to the next vertex. If it's bound, I'm going to put its parent as required, and this becomes free. And I do it for all these leaves. They become free, their parents becomes required. Then I go to vertex 8. If a vertex is required, I add it to the set, and if its parent is bound, that means it needs to be dominated, but if I've added 8 to the set, this becomes free. I don't have to dominate it because it's already dominated from below. So they change. 7 is free. As soon as a vertex is free, I move to the next vertex, which is 6. If a vertex is required, I've got to add it. And if its parent is bound, I change it to free. If its parent's free, I leave it as free. So what happens here is that this gets required, the parent stays as free. Vertex 5 is required, I have to add it. Once I add it, its parent, I change its weight to free, etc. And then I go to 4. That becomes added, parent's free. 3 is free, I can move to the next vertex, which is free. And finally, when I get to the root, if the root were bound or required, I add it to the set. And then I'm finished. And everything's handled, and the required vertices, namely the blue ones, form your dominating set. So essentially what the tree algorithm does is it pushes the vertices up in the tree. If at all possible, dominate with a parent. And what you will get is a dominating set. And in this case, you will get a dominating set of cardinality 5. And what you can prove, and we're not going to do it now, is that this algorithm will give you a dominating set, but it'll give you more than a dominating set. It'll give you a minimum set. It'll give you a gamma set. So that's essentially the algorithm. And you can prove it very easily that it's extremely efficient. You can find the set in linear time. So for some classes of graphs like trees, there are not only polynomial algorithms, there are linear algorithms that will find you a gamma set extremely quickly. So let me go back and stop sharing this. And are there any questions about that before I stop for a tree? And for some class of graphs, you can find the domination number very easily. So this is just an illustration. You root the tree, you start at the bottom, and you try and work your way up the tree, and you push up the vertices in the dominating set. And you can prove, which we haven't done, is that you can always find such an algorithm that'll give you a gamma set. So let me maybe stop sharing now, and we'll go back to our, let's go back to our exercises, which we'll work on together. So let me find them. So I think we had, so let me share the exercises again. Which ones did I have? Okay, hopefully you can see that. So what we've done is, now I'm going to get my iPad because we're going to work through some of these together. So we've done number 1 really, and we've done number 4, but let's work through the rest. Let's take...
Prof, please,
yes.
There's a question in the chat.
Yes, please do mention them. Okay.
Okay, so is it possible to get an approximate domination set for a graph G by considering the its spanning trees and applying the tree algorithm?
Exactly. You can do that. What you can do is you could take a graph, look at a spanning tree, apply the tree algorithm, and you'll get a dominating set. That's minimum for your tree, but in your original graph, it may or not be very good at all, but it'll be a start. What you can also do is what's called a greedy algorithm. Now, a greedy algorithm says the following. You start off with a graph and you do a greedy approach. You pick the vertex of maximum degree because that's going to dominate as many as possible. And you firstly pick that vertex in your set. And you pick that vertex and then you remove it and its neighbors. And in what's left, you pick the next vertex of largest degree because that's a greedy approach. It dominates as many as possible. You pick that vertex and you remove it and all its neighbors. And you keep on going, and at every stage of the algorithm, you simply do a greedy approach. You pick the vertex that dominates as many as possible in the remaining tree. When you finish that algorithm, you can show that the set you get will have cardinality 1 plus log delta over delta. It'll be so the greedy algorithm will give you a dominating set of cardinality 1 plus log delta over delta times the order. So there's many approximation or greedy algorithms, or there's many approximation algorithms you can do. But the one you mentioned for a tree is no problem at all, but it depends what spanning tree you get. If you do a depth first search and get a spanning tree by that, it may not be so good. If you do a breadth first search, it may be a little better. And then you use your very quick algorithm, get the dominating set, and go back to the original graph. The problem is it could be very far out. But there are enormous amount of approximation algorithms. I said the greedy algorithm. There's many such algorithms which are extremely useful. Some are not very good, but some are very good. So any other questions about that, about the tree algorithms or any other approximation algorithms?
No other question from the chat.
Okay. So maybe let's get to maybe one or two of the interesting ones and just work together. Let's take number 2. I mean, minimal sets are normally very easy to find, but just to clarify the definition. So let me see if I can hook up with my tablet. So let's see if I can sign in here. And then we can work through some of the exercises. I'm going to stop sharing here, and I'm going to see if I can share with my tablet. Let me see if I can start sharing here. Okay, I'm not sure if you can. Let me find a screen. Are you able to see that?
Yes, we can see as well.
Okay, so let's take the first exercise. I mean, just one example. Suppose I give you, let me see how I get this going. Sorry. Let me take this little example of K33. Let's take K44. And let's just look at a minimal dominating sets. How many minimal dominating sets can you find? So if you try and dominate, for example, okay, let's just pick one there. You got to dominate, you could pick the bottom one and you agree that's dominating set. Everything's dominated. So everything's dominated and that's minimal. Or I could have picked maybe something a little different. Let's go back again. What if I'd picked this set? Now that's also minimal dominating because everything's dominated, but it's minimal because every vertex is its own internal private neighbor. It's a minimal dominating set. So for this example, for example, of K44, there's two minimal dominating sets. One has got cardinality 4, one's got cardinality 2. So minimal doesn't mean minimum. I mean, if I wanted a minimum set, I would have rather gone for this set. But both are minimal. And if, for example, let's just take that this 5 prism as another example. So let's take this little graph. Let's take the 5 prism just to illustrate the definition of minimal. So if I gave you, drawn it very badly, but let's take the 5 prism. Let me add in. So how many minimal dominating sets can you find with a 5 prism? So minimal with respect to Auro's lemma, that every vertex is needed for some reason. I mean, you could pick many. I mean, it's probably many examples you could, let's just randomly, that dominates those 3 neighbors. I could pick, for example, this one. So what's not dominated? I've got 2 vertices not dominated. I could pick that. That's an example of a minimal dominating set because these vertices are needed to dominate those. This is needed. So that has 2 external private neighbors. This is its own internal private neighbor. And it has 3 external neighbors. But he has 1 minimal dominating set of cardinality 3. But you can find one of cardinality 4, for example. Maybe I could have picked, let's try, what if I'd picked all the outer vertices? That's also minimal dominating because I need every vertex. If you take one of them away, it doesn't dominate because now there's a vertex over here that's not dominated. So this is a minimal dominating set of cardinality 5. And you can also find one of cardinality 4. I mean, let's just take, all right, let's pick this one. Maybe pick these 4. Now, again, this is needed to dominate that. That is needed to dominate the one outside. This is needed. So all those 4 are needed because they've all got an external private neighbor. So yeah, just this very simple example, you've got a minimal dominating set of cardinality 3. You've got one of cardinality 4, one of cardinality 5. So what you've got here is that the domination number, those in fact all you can get is between 3 and is equal to 3. But you've got many different kinds of minimal dominating sets. And what you want to do is find a minimum one. So you wouldn't go for this, you'd go for one of a minimal one of cardinality 3. So do you understand the definition of minimal? Minimal is not necessarily minimum. This is minimal. I need every single vertex by Aura's lemma. I can't do without any vertex, but it's not minimum. I could have picked 3. So is that clear? So that's just to illustrate the definition of minimal. In fact, while we're on, so everyone happy with that? Let me maybe, just while we're playing around with dominating sets, if I gave you a simple example, so I think that example 5 I gave you, let's take the generalized Peterson graph that I gave you at the start. Remember, it's got 7 vertices. Okay, I'm probably not drawing it very well, but let's take this generalized Peterson graph, which I've drawn very badly. And I've drawn it extremely badly, but and let's just add in the edges. So you've got your generalized Peterson graph. And remember, you jump. This is one way I'm going to jump. I'm going to jump 1 every time. So this is graph. If I asked you for the domination, can you prove to me that it's 5? How do you prove it? Without Reed's theorem, without anything. Let's suppose you know nothing about domination. How do you prove to me that the domination number is equal to 5? Any ideas? So there's 2 things. You've got to prove a lower bound and upper bound. The upper bound is very easy. You can just find 5 vertices that dominate. So, I mean, let's just pick any old 5. You can very easily find 5. I mean, let's pick this blue one. If you pick these 5, for example, as we did in the lectures, that dominates. So it's very easy to find an upper bound. You just give me a set. And those blue vertices will dominate. Every vertex that's not colored blue has a blue neighbor. So that's easy to do. You could find many others. This is not unique. But how do you prove to me that the domination number is at least 5? How do you prove that? Well, let's do it. Let's take a dominating set. So let D be a gamma set of G. So it's a minimum dominating set. So the dominating set is a coordinator D. And let's prove that D must have at least 5 vertices. So how would you do that? How would you show that any dominating set has at least 5 vertices? Okay, there's many ways, but let's look at one way. Let me see if I can get some more space. Oh, how do I create a new page? Let me see if I can get a... Okay, excellent. Let's take a dominating. Let's look at 2 cases. So case 1 is just a simple counting one. Let's suppose that in the set induced by the dominating set, there are no isolates. In other words, what I'm assuming is that in this dominating set that you pick, we don't know how many there are, but we're assuming that every vertex in the dominating set is adjacent to at least one other vertex in the set. That's case 1. If we do that, then we can do some simple counting, because the graph is cubic. The graph I gave you is cubic. So that means that every vertex has at most 2 edges coming out of it. You agree? So if I count the edges coming out of D, it's at most 2 times the cardinality of D. You agree? Because I'm assuming that everything in D has one neighbor inside D at least. And because the graph's cubic, it has at most 2 neighbors outside. Now the graph is dominating. What does that mean? That means every vertex outside is incident to one of these, at least one of these edges. So that means that the number of vertices outside is at most the number of these orange edges. Because if everything's dominated, everything in V minus D must be incident to one of these red or orange edges. But there are at most 2 times the cardinality of D orange edges. And this is n minus the cardinality of D. So what we get is that n is less equal to 3 times the cardinality of D, or equivalently, D is at least n over 3. But what is n? Well, n here is 14. Now, the domination number is an integer value. So, of course, this is all the ceiling. So the ceiling of 14 over 5 is 5. So in this case, if the dominating set D is such that every vertex in D has another neighbor in D, then we know that the domination number is at least 5 by simple counting. You agree? So that case is easy to handle. Just do simple counting, counting edges coming out of D. Because it's dominating, everybody outside is incident to an edge, to one of these red edges. Just do simple counting. You're going to get at least 5, at least n over 3. Okay, what happens in case 2? So let's take case 2. So case 2 is that the subgraph induced by D contains an isolated vertex. Let's call it V. So in the set D, there's some vertex V, and all 3 of its neighbors are outside. Now, I don't know what happens in the rest of D. I have no idea. Could be some other like that, some like this. I have no idea. But there is a vertex that has all its neighbors outside. So what we're going to do is the following. We're going to remove from the graph V and all its neighbors. Call the remaining graph G prime. So G prime is G minus the closed neighbor of V. Because V dominates those. And in this remaining graph, let's call it the blue graph. Let me go, I should go down a bit further. Sorry, let me go down a bit further. Oh, it's not so good. So sorry, in the blue graph, we know that the remaining vertices of D, which I'm going to call D prime. So D prime is D minus V. Those dominate. What we've got to show, so what we know is that the domination number of G, which we chose as D, D is D prime plus 1. What I'd like to do is prove that D prime is at least 4. And if I can do that, the domination number is at least 5, because gamma is at least D prime plus 1. So how do we prove that D prime is at least 4? Well, that's going to be fairly easy. So let's look at our graph. So if you don't mind me quickly redrawing it, let's take our generalized Peterson, which I'm not going to draw very well, but let's look at the drawing of it. And let's take our graph. So again, what we've got, very bad drawing. Here's our generalized Peterson. Two, 4, 6, 7. Hopefully I've drawn it okay. So what we've got is, we've got 2 types of vertices. That one's in the outer cycle, one's in the inner cycle. Complete symmetry. So there's two cases to look at. This vertex V that belong to that dominating set may be in the outer cycle. And when we remove it, what do we get? We take away V and we take away its neighbors. What are we left with is this graph. Now, let me redraw it. This is a bit of a mess. If I redraw it, what we get, and it's very easy to check, this is what we'll get. We essentially get 2 5 cycles. And then you'll get 2 vertices outside joined in this way. So this is the graph obtained by removing that vertex. Now, this is what we've called G prime. I've taken V and thrown it away in its neighbors. To dominate this, we need at least 4. And that's easy to see because there's a few possibilities. How do I dominate those vertices? Well, one option is I could pick this one and this one. That dominates that, that dominates that. But then I'm in trouble. Because how do I dominate this vertex? And how do I dominate that vertex? They're so far apart that I need 2 more vertices. So in this case, you can easily check that you need 4. Because to dominate that one, I need 1 vertex among here. And to dominate this vertex, I need another vertex. So I need at least 1 plus 1 plus, I need 4. What happens if, let's go back again. What happens if in the situation that we had initially, what if one of these went? Then again, you need 4 because you can easily say, this one you could just push out. That if that was in, you're back to, if this was in, I could just push this vertex there. So I can assume that is not in. If this were in, for example, I'm again in trouble because these 4 vertices, I've got to dominate those 4 vertices. And I need 2. You can't do it with 1. So again, you need at least 4. I've got 1 here, 1 there, I need 2. And in all the cases that you check, you can very easily convince yourself that, for example, if this vertex were in, again, I'm in trouble because now there'll be these 5 vertices, these 4 vertices. And again, to dominate those 4, I need at least 4 vertices. So it doesn't matter how you look at it, you're going to need 4. And then that means that going back to what we did originally, what you've got is originally we showed that your domination number is at least is D, which is D plus 1. If coordinated D prime is at least 4, then you show that you need at least 5. So you can prove that with a little bit of case analysis that for the generalized Peterson graph, your domination number is at least 5. Of course, with a property of reads one, we could do much better, but you can very easily, just by playing around, you can check that your domination number is at least 5 and it's at most 5, and therefore it's equal to 5. So that's essentially what you would do there. So that's, I mean, just playing around with some of the domination. Maybe there's many other exercises, but maybe let's, can I give you one more? Are there any questions on that one? I was wondering if I can just do one other exercise together. We haven't got much time, but this is just playing around with some examples. Let me go back, if you don't mind, to our, let's see if I can stop sharing this somehow. Aha, okay. Let me go back to this following question. If I just share this screen with you. So this, We've got a few more examples here. Question 6 would be interesting, but maybe we've just got time for one more. Let's look at number 8. Can you find me an example of a planar graph with diameter 2 and domination number 3? Or even at question 7, can you give me a graph with very small diameter and give me a bound on the domination number? In this case, the domination number is most delta. And that's extremely easy to do. But then we're going to look at question 8. We'll finish with that. So question 8 is, I want you to give me an infinite family of graphs where everything's very close together, diameter 2, but the domination number can be arbitrarily large. So can you find that an example of that? Let's maybe look at that. Can you think of an example of diameter 2 and arbitrary large domination number? So let's maybe look at such an example. We'll construct it together. So let me give some examples up here. Let me share the screen and we can look at an example of that. Let's take this example, which you may be familiar with. So what I'd like to do is just give you a construction of a graph which has diameter 2. Everything's really close together, but the domination number can be extremely large. And that's this Cartesian product that you may be familiar with. So you pick 2 graphs, pick your 2 favorite graphs, and you form what's called the Cartesian product. The vertex set is the product of their vertices, V of G times V of H, and 2 vertices, G1, H1 and G2, H2 are adjacent if known if either they equal in the first coordinate and H1 and H2 are adjacent in H, or the other way around. Maybe H1 and H2 are equal, but G1 and G2 are adjacent. So let's just take an example. Let me take as H a 4 cycle and take as G a triangle. Now, when you form the Cartesian product, essentially you're taking multiple copies of G and H. You have what's called layers. So for this graph G, for every vertex of H, you've got a copy of G, which we're going to call a G layer. And for every vertex of G, the way I've drawn it vertically, you've got a copy of H, which I call an H layer. So you've really got 3 vertices of G, and that'll give you 3 copies of H. And for every vertex of H, you'll get a copy of G. You'll get these H layers. So this is your graph. So what we're going to do, let's see if I can. Okay, so what we want to do is if I go, I should have given you a simple example, but if I take the Cartesian product of 2 cliques, so let's just imagine that on the left, I've got a complete graph, which I don't, yeah, it's 4 cycle. If I give you 2 complete graphs, or any 2 graphs, what is the domination number of the Cartesian product? So here's a graph. Let's take G of n vertices. Take it a complete graph, and take H as a complete graph and n vertices. Just imagine it. Yeah, they're not here. So there's n vertices in H, n in G, they're both complete. Look at the Cartesian product. The diameter is 2 because you can go for one vertex, you can jump to any other vertex in one, and then jump to the vertex in H if it's complete. So if this graph were complete, I can get in 2 steps to any vertex. So the domination number, what would it be? The diameter is 2. What is the domination number? If G is complete and if H is complete, and you look at the Cartesian product, you get all these different layers, I'm claiming the domination number is at least n, where n is, so if G's got a clique of order n, H is a clique of order n. And the reason is that if you take any copy of G and any copy of H, so let's take, for example, this copy of G corresponding to H2, and take the copy of H corresponding to G2. If there is no, and take a dominating set of the Cartesian product. So in this Cartesian product, take a dominating set. If it does not contain a copy in this fiber and in this G fiber here, then that vertex, G2H2, would not be dominated. And that would be a contradiction. So what we can argue is that if you take the Cartesian product of two complete graphs, then every fiber, let's say G, must contain a dominating vertex. Because if this didn't contain a dominating vertex, then every H fiber would contain a dominating vertex. So your domination number would be at least n, where n is the order of G, the minimum of the order of G and H. So in this way, I can construct fairly easily, if you take G to be a complete graph order n, and H to be a complete graph of order n or bigger, you can show the domination number is at least n. And it'll be equal to n because you just pick a vertex down the diagonal if the coordinate fits to equal. You can prove that the domination number is at most n and it's at least n. So this would, you can construct graphs that have small diameter 2 and their domination number could be arbitrarily large. So if I drew you a picture, let me stop sharing this and go back to the iPad. You could very easily find, let me go back and we'll close with this. Let me go back to this iPad. I'll just quickly share, and then we'll stop with that. So let's see if I can share this quickly. Let me get this screen up. Okay, so if you'd let me in, but otherwise we can, doesn't matter if I can't get in again, but that'll be an example where if you take the Cartesian product of two complete graphs, you can find a graph with domination number arbitrarily large and diameter 2. So that was just an example to give you a class of graphs. So I think we've run out of time, but we've just scratched the surface of domination. So are there any questions before we stop? And I'll go back to the exercises and we'll stop there. Let me just share the screen of the exercises. So we've just touched on the exercises, but let me stop there. Are there any questions about the basic concept of domination?
Please, there's a question in the chat. It says, can you say something about the cube graph of order n greater than 2?
Sorry, of which graph? Of the n cube?
Yeah, cube. Yeah, the n cube graph.
The n cube graph, we don't know the domination. We do know the n cube is a Cartesian product built up, say K2, Cartesian product K2, and you keep on going. You build it up. It's a very nicely structured graph, very useful for coding theory, but we only know the domination number in certain cases. So there's a class of graphs where we actually don't know the domination number in general. We do know for special cases, if it's to the power of 2, if it's the cube, n cube, qn, where n is 2 to the power k, we know what happens. But in general, for the n cube, we actually don't know. We've got bounds, good lower and upper bounds, and for some values, we know exactly what it is. But in general, we don't know. So there's some very simple classes of graphs like the n cube where we simply do not know what the domination number is. Special cases we do.
Okay. Well, so I think maybe that also answered the second question, but I think maybe we can add more. So the second question is, what are some of the open problems in this area, and what are the active directions?
Okay, so there are many open problems. The one we've just done, the Cartesian product. So the Cartesian product, if you remember what we've done, we've got to take a graph T, a graph H, any two graphs, form the Cartesian product. The most outstanding problem in domination is a 58-year-old problem. Let's call it a 60-year-old problem by Wiesing, and it says that the domination number of the Cartesian product with G and H is at least the product of the domination numbers. So the domination number of G Cartesian product H is at least gamma G times gamma H. That's a very famous problem. I've worked on it for 35 years. I've spent tens of thousands of hours on it. It's open for almost 60 years. That's a very big problem. If you can solve that, you're doing extremely well. That's one of the big ones. Domination in cubic graphs, as I said, if the order is very large, we don't know what the supremum is of gamma of the order if you take the limit. That's a very big problem. The girth one, as I mentioned, if the girth for a cubic graph, the conjecture is if it's at least 6, what is the domination number? I've worked 12 years on it, and I think I can prove with some French colleagues, but again, we've already got a well over 100-page proof. We think we can prove a third n if the girth's at least 9. And that's just on bounds. There's many, many other problems one can look at. There's many, many problems in domination theory, many algorithmic problems. So there's many, many open problems on domination that we just don't know. There's one of my old PhD students, he's got a computer generating program that gives you all these conjectures, thousands of conjectures on domination. And he's generated also thousands of conjectures. So there's just so many problems on domination theory. Some are very difficult. For example, as we saw today, minimum degree at least 4, what is a best possible bound for the domination number? We don't know. It's at least a third. It's at most 71 over 200 times the order. We don't know. So there's just for large minimum degree 4, 5, 6, we don't know. For minimum degree at least 6, we know it's at least a quarter the order. It's at most 3/10 the order, roughly. We have no idea what the best bounds are. So we're very far away from best bounds. So those ones get extremely difficult. And then, of course, there's different domination parameters, independent domination. Enormous amount of problems there. How does it relate to domination? The ratios, there's total domination, which is a huge area. And there's a very good interplay with hypergraphs, which I haven't even mentioned. And there you go into hypergraph theory. And you use transversals to solve it. So there's a huge branch of domination theory in graphs using hypergraphs. And then there's Roman domination. There's all these different domination parameters. So it's vast areas. Today, we've just focused on the core parameter gamma. And there's hundreds of unsolved problems. Some are very, very difficult. Some are open for 60 years. There's some extremely difficult problems. So those are just a few that I've just mentioned. But there's some very difficult open problems in domination theory that one can work on.
Okay, bro.
So that's just a very few that I can mention.
Okay, thank you. There's another question. Are there applications of domination theory to game theory?
There are, but I work enormous. I've just written a book on domination graph games. So game domination theory. And again, there's many problems of domination games that I won't even go into. But it's a 2-player game. And you've got someone called dominate and you've got someone called staller, and you alternate. And every move you make must dominate somebody new that hasn't yet been dominated. But dominator is trying to create a set as small as possible. Stall is trying to create a set as large as possible. And then you look at what abounds in the domination game. And there's very big open conjectures there. The 2/5 conjecture by Douglas West, for example. That is it true that for the domination game, it's always at most 2/5 the order? And we don't know. For total domination, the conjecture is 3/4. We know a lot, but there's an enormous amount we don't know. So there's many domination games that are, and they use this continuation principle. So it's a huge area of domination theories, domination game theory, a very big branch of domination. I've written a book on that. I've written a book on 2 books on total domination, and also one on with interplay of hypergraphs. So there's enormous areas of open problems in those areas. Some are very challenging, and we still don't know the answers. So there's many open problems. So the book on topics and domination mentioned about 18 fundamental domination parameters, like connected domination, restrained, and each one is many open problems. Some are very difficult. And then there's the structural graph theory. There's a lot of problems there, algorithmic problems. There's domination in digraphs. There's probabilistic methods that Paul will speak about tomorrow. There's random graphs. But today we've just focused on gamma, the very basic elementary property of domination. So that's just a very basic introduction to domination theory.